In this video, we're going to discuss logistic regression. We're actually going to go over some of the points with logistic regression. It's you use it to calculate the probability of a given event based on one or more factors. And it's not like regular regression where the coefficients are a unit change in a coefficient equals a particular change on the y-axis. In this case, we start talking in terms of odds. And let's just remind ourselves what odds are, and that's the probability of an event divided by the probability of that event not occurring. It's a binary type of situation. And so what are the odds of flipping at least one head? Well, you can have a head-head, a head-tail, a tail-head, or a tail-tail in the case of two coins. Three events have at least one head, and one has only tails and no head, so it's a non-event. And the odds ratio, or the odds rather, is 3 to 1. An odds ratio is the ratio of odds under different conditions. So in a logistic regression equation or situation, you have those, the y is an odds ratio because the different conditions are the various levels of independent variables. You get the odds ratio from this for each regression of coefficient. So by exponentiating, because we've taken, well, we're going to talk about this, but we've taken the log to get at the odds ratio. It's e to the b, and because when we talk about logistic regression, we're using something called a logit, and I'll show you how that works in a second here. But it's the log of the probability of an event divided by 1 minus the probability of an event. That's the odds. And then it equals a plus bx. And when you get b is in a situation where the value of x, there's a certain weight for it. And so you get that value over not having that value, and that becomes an odds ratio. You can, it's a little confusing, but we'll try and clarify this in a minute. The probability, you can solve for p and find out the probability of a particular event given a particular condition with the formula e raised to a plus bx over 1 plus e to the a plus bx. So that's the regression formula exponentiated in this fashion. Another really handy feature is to determine the 50-50 cutoff point. In other words, if we're looking at something, where's the point at which half the it's 50% likely to be above this criterion and half below. Well, that's a logit of where the probability is 0.5. So 0.5 over 1 minus 0.5 is the log of 1. The log of 1 is 0. So you solve for 0 equals a plus bx. You solve for x. And that equals x equals minus a over b. So let's take a look at what our issue is in logistic regression. Now we said that we want to do a y equals a plus bx, but in this case the y is binary. And so our raw data, if we look at zeros and ones, if we were to plot it, let's say we have an observed score, it looks like it goes from 0 to 100 or something like that, and we see that we just get 2 points. It's really not something that has much information in it. Now, if we were to, in fact, do the probability of an event, now this is a predicted probability. The actual probabilities are a little messier, but this is to show you that this is the relationship between probability and the observed score. Now, what do we notice about that curve? when we're thinking about trying to simulate linear regression. We can see that the probability is not linear. It has this S shape. So we have to get rid of that S shape. And how do we do that? We transform the equation using the log. And so we use the logit, and that's the log of p over 1 minus p. And that, as we can see, if we take the middle curve, if we take this curve right here, and we transform the p into log p 1 minus p over 1 minus p, we get a straight line. Now we can fit a linear regression curve. And again, like I said, these are the predicted values. The actual data is a lot messier. As you can see over here, the values down here kind of overlap these. So there's mess that is not picked up when you just use the prediction. But this is the model, and we can look at how well the model fits in other places. So we do logistic regression by converting raw data to a straight line. Now, for our example, we're going to do the BIV study, and that's a brain injury vision symptom survey. And that was a test, a symptom survey developed by Dr. Hannu Laukkanen. And it's a set of 28 questions. And the answers, there's 28, so it ranges, actually, I have said the range is 0 to 96, but we only use 24 of the items, so that range is 0 to 96. And each question is a Likert scale, 0 to 4, never, seldom, occasionally, frequently, always. There are 8 dimensions here, and 8 dimensions actually come out if you do the Likert analysis, pretty close to what these are. But we wanted to use a Roche analysis because our data are ranked. However, they are also normally distributed, so it was perfectly reasonable to do a factor analysis. And in the paper that was written in OVS, we did it both ways, and it shows the reasonableness of both arguments. The thing is, the dimensions are not they're good dimensions, but the overall dimension, single underlying primary dimension, if you drop 4 items, is not all that bad. It didn't meet the criteria to reject a primary dimension for Roche analysis. So we actually do it both ways. In the example I'm going to show you, we're just going to use the total score from the BIVs, the 0 to 4 scores rather than the Roche numbers, just because it's a little bit easier to understand and the point's still made. We validated this test using first and third year optometry students, TBI soldiers, TBI patients, and stroke patients. In the OVS article, you can check out, they were just optometry students and TBI patients. But there are questions like distant eyesight clarity, distance vision blurred and not clear, even with lenses, and so forth. And so you just find out all the symptoms and add them up, and then we do this. Now, one of the questions that we had with the total score is there a cutoff point? You think of the convergence and sufficiency scale, and that cutoff point is at 16. Here we do a logistic regression, and the regression is, are you TBI or not? And then you have your score, and we do the logit, and we get a logit as a function of a plus bx. Now, if we want to find out the cutoff, we can solve for the probability at 0.5. So remember the logit is the natural log of 0.5 over 1 minus 0.5. Well, 0.5 over 1 minus 0.5 is 0.5 over 0.5, or 1. The log of 1 is 0. So we can solve for 0 equals a plus bx. We can solve for x. And x equals minus a over b. In the example, and I'll do this in a minute, the regression equation comes out with the intercept equal minus 3.878. The intercept is, or the slope is 0.119. And so the 50-50 cutoff is minus 3.878 divided by, that should be 0.119, is 33. The totals above 33 suggest a problem. So if you score, we can see here we're at 33. That's at 50%. People below are saying don't seem to have a problem. And while we call this TBI, it could be that, I mean, we use TBI to validate, but you could score high and not have TBI. But you would have a problem from a symptom sort of looking point of view. But here above above 33, we're above 0.5 in probability. As you get higher, the probability of you having a problem is greater. If you're below 0.5, the probability and your score goes down, the less likely you have a problem. Okay, let's go into an example. Let's see how we do this. And I have in this data set, I have the score for the person. So we have zeros, ones, twos, threes, kind of rank ordered up to about 89. And then we also have the TBI. You can see we have 1 if you had TBI, 0 if not. Now, here we rank ordered those scores, and you can see we have ones and zeros mixing in there. So this is where our prediction was not perfect. And so let's do a regression. Analyze regression. We did this before, we've used linear. Now we're going to go to binary logistic. And our dependent measure is going to be TBI. We go down, we find TBI. That's the 0, 1 variable. And our total Likert score was up here. That's the observed score. That's that variable. Now, we want to save our probabilities because we can do that formula that the probability equals the exponentiation of a plus bx divided by 1 plus the exponentiation of a plus bx. But SPSS is kind enough to do that for us, and so we're going to ask it to do that. Now, okay, under options, what do we have? We can test the goodness of fit. It's probably not a bad idea. And let's leave it at that. And okay. So what do we get? We have, it says there were 264 cases. There were no missing, so we had scores on everybody, and we had whether or not they were TB on everybody. That's pretty good. It's always a good idea to make sure that SPSS is coding like you think it is. This will come up sometimes where the original value is 0 and it gives a 1. For example, if we had 1 and 2, it would give the non-TBI person a 1 and the TBI person a 2. And that would be confusing. The classification table, this is 0 beginning block. It doesn't do any fitting. That just kind of says where you are at the beginning, tells you how well you're fitting the equation at the beginning, and the significance being small means that we're not fitting it very well. Then these are all the tests that are, and this is different from least squares. This is a maximum likelihood method, and rejecting the null hypothesis is not a particularly good thing. There is no such thing in maximum likelihood as computing an R squared. But there are these little measures that simulate an R squared. We're not going to go into the calculation of these, but just know that they're out there, that trying to give you the idea of simulation. And, that's somewhere between 5 and 6.5 and 0.5 and 0.6.5 for R squared. Not too bad. The Hosmer-Lemeshow test breaks the scale down into pieces, and the idea is if any one piece is weighting the whole thing, this will be significant. The fact that it's not significant is a good sign. So we don't want the Hosmer and Lemeshow test to be significant. That would reject our model of being a good fit. And this gives the contingency table of telling where everything is. You can see that it breaks it into these categories going from a low score to a high. And we can see by the frequencies here that if you don't have TBI, you have pretty high frequency going down to not so much, as opposed to the other end. If you do have TBI, your scores are not so many at the low scores, but go up to a lot at the higher scores. In a classification table that it comes out, we observe 0 and 1. So 157 people did not have TBI, and 24 plus 83, or 111 people, did have TBI. And then what did it predict? It predicted 148 plus 24, 172 did not have TBI, and 92 did. And it correctly predicted 148, which is 94%, did not have it. That's specificity. And it predicted that 83 did have it. That's sensitivity at 77. The overall accuracy, if you look at the correct, which is 148 plus 83 divided by the total number, is 87.5%. And then this is our regression equation. Notice the constant is down there. This is the A part, A plus BX. This is the A. And that's in the numerator of our cutoff. That was the minus 3.878. And this is the denominator, 0.119. All right. And these are both significant. So the variables is significant. And if we exponentiate this b, we get an odds ratio of 1.126. Now remember, 1 is nothing. And you would think, well, actually, we haven't found much here because it's only 1.126. But remember, this is on a scale from 0 to 96 on our x-axis. And so as we increase 1 unit on the x-axis, we're increasing our probability, our odds ratio rather, by 0.126. So you don't have to change very much before you're getting into a pretty big odds ratio. All right, that is the that is it. I don't think I have anything else to say. Thank you.